the lesson. All right, so today we're going to continue on our review of exponential functions, but today we're going to look at the application part, which to me makes the most sense. Why would we bother learning this? What would we ever do with it? Okay.
Stock.
We can look at frog populations as well.
We could do math with it.
I do math with exponents, especially anything that has an interest rate to it. Like, you better believe this girl always reads through every line of her mortgage statement. And I found 2 mortgage contracts that were wow. It's fun to have a math teacher. Let me explain to you why these numbers don't work. So, all right, so sometimes it helps to understand, if you don't want to pay an extra $5,000. All right, so here we go. Y equals A times B to the x. This was our general form for exponential functions. A represented the initial amount, right? Do y'all remember that from last year? Great. B is our multiplier. So it can take the form of different things. So let's talk about the different things we looked at last year. The first thing is when we had a percentage. We would do either plus or minus the percentage, depending on if our if the example we were modeling was growth or decay. It would be 1 plus the percentage, written obviously as a decimal, and 1 minus the percent if it were decay. All right, then we could actually have like whole numbers in here. So if we saw the word doubles, the population doubles, what would the multiplier be? 2. Or if we saw words like triple, what would the multiplier be? 3. Or if our example involved half-life, 1/2. Okay? So these were some of the multipliers we used last year. Now, x represents the number of time periods. All right, so if we go back and think about our multiplier, in these problems, if that multiplier, if in our real world example that multiplier is greater than 1, this would be an example of exponential growth. Good. And if that multiplier were between 0 and 1, it would be an example of exponential decay. Okay, so today our first one we're going to do is on the worksheet. It was the front page, number 12. Talked about a population of, we're going to change it because frogs is not popular today.
Turtles.
Sure. Population, 100 turtles.
130.
Is that better?
Can we make it like Harry?
All right. Yeah.
Turtles.
Everybody loves peanuts. Peanuts taste good.
Really?
Who said that?
Mr. Wilby, I once had an extremely vivid dream when I was a penguin. And I mean,
Last night.
very, very
Okay.
I remember that.
It was awesome.
Every day in this job is different. Every day. Who knew I was going to hear that today? When I woke up this morning, I did not envision that occurring when I thought today I teach exponential functions. We'll discuss how penguins taste good. All right, so
Should they would?
The whole website
I don't think so
about
either.
penguin restaurants.
That's why
Right.
it's increasing.
a population of 100 turtles decreases at an annual rate of 22%. This is sad because our poor little turtles are dying off. How many turtles will there be after 5 years and 10 years? How long will it take the turtles to reach half their original amount? Okay, so first thing we're going to do is we're going to write an equation that models this situation. So we have our population of our turtles with respect to time. Population with respect to time. So what was the initial population of our turtles? 100 turtles. it says that we are decreasing at a rate of 22%. So decreasing would be 1 minus, and we always take that percentage and rewrite it as a decimal. So that would be 0.22. And we would let t be our exponent, where t represents time in what unit?
Years.
Good, time in years. Okay, so this is a great exponential function that represents this, or models this situation. So the first question, how many turtles would there be in 5 years? So we're finding p of 5. Okay, we'll punch all this straight into our graphing calculator all at once, and it gives us approximately 28.87 turtles. Okay, but a turtle is a living creature,
Yeah.
and therefore a discrete quantity, correct?
Yeah.
It's not really measurable, it's discrete, it's countable. So when we have those, our situation models something that's countable, we generally wouldn't leave our answer like this. Now, if it was something that was measurable, like weight or speed or measurable things, then we could leave our answer like this, but this is not measurable.
When you just say approximately.
So, instead of, we could say approximately
We also can't
28.87.
have 0.87 of a turtle.
Right. This is our problem.
Well, not.
So, what we're going to have is 29 turtles. When it's an exponential decay, I'm going to round up because I haven't made it down to the 28th turtle yet. We have one that's still hanging on.
Oh, the other way around for exponential growth?
Correct. Exponential growth, you round down. Exponential decay, you round up.
That's cool.
Okay?
Exponential growth you round is
Up is
right.
down, down is up.
Yeah, up is down, down is up.
Makes sense.
You just gotta
But
remember
we
which way
only have to do that if our scenario involves a quantity that is truly a discrete situation,
Like the turtles.
like turtles or people,
Penguins.
population. Yeah.
I really wish I showed some animal that people didn't love. For this purpose.
All right, so yeah, now we're down to 29 turtles. All right, you try to discover what the population will be in 10 years. How many sweet, sweet turtles will be left?
Don't say it like that, I feel bad.
We should have made it like snakes.
8.
Only like 4 people in the world like snakes,
I
though.
like,
9.
See, 1 of 4.
that's not a measurable number. You have to round it out. Or down. 8. Depending on whether it's. I like those. Have you seen the video?
I got there to be 9.
Why are we just assuming that like these
So,
turtles do not have
even if
years?
it is like 8, like 0.3,
These are
You would still
lonely
round up?
turtles.
Like, I feel
Um,
like the turtles would not.
Correct.
All these turtles are having terrible balance.
Generally, when something like this happens, there's something in the environment causing the die-off. Yeah.
School. What's really weird is with how long turtles usually live. They're dying off.
Yeah.
Turtles was the worst
Okay,
demographic
so
to
if it's
use.
0.34, you still round up.
Yeah. Yeah.
So it's like 0.4.
No, that's right, yeah. Even the way you said it.
Like a tiny bit of the brain.
Okay, now,
Yeah, it is.
the other thing we did when we looked at exponentials, what was we solved them. So we might have asked I might have asked you, how long will it take for the turtle population to reach half its original amount?
Yeah, good job. I did it.
Okay, and so how would we do that?
You just.
Isn't there a good
Yes,
way to do that on a calculator?
That's what I would have done.
You would do what?
No, this, I don't know if this, we have a quiz. Can't you chart this in a calculator?
You can. What I would do right now, what we know how to do is take and set these equal. And then we're going to shift this entire function back down to the x-axis so we can check out the zeros. Haven't we been doing that recently?
Yeah.
Oh.
Now,
it's
pretty
not really
soon, we're going to learn how to algebraically solve this without having to do it graphically. I'm using logarithms. Yeah, and actually, I think you'll enjoy it. It's approximately 2.79, and I thought I heard somebody say that, which was pretty cool.
Absolutely.
Nice. All right. So now I'd like you to try number 10. Then set yourself, write yourself a reminder to charge it.
I need to. I have a friend who usually
Put a sticky note on top of
calculator.
Well, I mean, if we have math homework that involves
Yeah, I use this thing
calculator,
daily.
That's true. That's true.
like
Yeah.
just the math homework involving calculator,
Yes. Then she's probably saying, you're right, you're right. Very, very sparse flurries at the moment. Sparse. Sparse.
It's supposed to freeze later tonight.
I
Yeah.
feel out to keep us for soccer practice if it's
Do we have to play soccer in the snow? I swear, I'm gonna die.
snow.
How'd your
No.
varsity game go?
It's probably Mercy World.
Is that like 10 to 0?
You guys,
Yeah.
you guys can play a sport that can only be played in basically one type of condition, like this.
Wait, where
No,
are
it can be hot.
Here.
It can be hot in the summer.
It's like 30
If
minutes.
it's wet, you can't play.
Because if it's north,
It's too dry in tennis. Oh no, it's like my sport, tennis, you can't play.
I'm pretty sure
If it's windy, you can't really play.
yeah, they had, there was no way that they
Barely.
The goalie tried to punt the
I mean,
goal
people
kick.
you play in the wind, but it's hard.
Yeah, I know. It's being
It was interesting.
I mean, you serve over here and the ball's.
You like this stuff, don't you?
Get it.
Yeah, this is, I like this.
This is.
Hey, easy. That's what you should change your attitude.
Okay, since it's exponential.
Is he too positive for you today?
Since it's exponential growth will be plus.
That is such a negative.
Well, plus 0.0.
All right, think about this one.
I was captain.
I don't know what that means.
Think about our problem. Do we have to round up or down?
No.
No. Very good. Good. It's measurable.
I wish we could go back in time before calculators were invented, so then we wouldn't have to do this.
No, we just have to do it by hand.
No, then we just.
What would happen is, in the back of our book, there would be these tables. They're called log tables.
So never mind.
And we would have to do 4-digit. Yeah. You'd have to do what I did when I was in school. Because I went to a not as wealthy school, and we didn't have class sets of calculators. So we did everything by hand. It was okay. I'm pretty good at mental math.
But now you're
Do you
smart
guys not
enough.
use those thingies?
At my school, school, yeah, mental math.
But math also makes you mental, so.
I'm not quite that old.
An abacus?
The abacus was slightly outdated by the time I entered high
But you
school.
didn't have calculators.
I
Like,
just did everything by hand.
I assumed just went hands, abacus, and calculator. Am I wrong?
We didn't have.
There's a long
I was
time.
so used to abacus. I'm with.
I do have a slide rule, if you'd like to see that.
I really used for this class to try it out.
Well, how about the shattered rain?
Is it responding?
Well, that's because she knows you're in school and you shouldn't be texting. Put that away.
She.
Whoa, what's that?
It's a
Emergency.
slide rule.
Slide what?
Slide rule.
It's an emergency.
How's that work?
You
There are
slide it
very,
on
very,
against the
very
gate.
few true emergencies.
Harry,
What?
for the ESL, that's when it's really cool.
Slide.
If you need a longer distance, you slide it.
I wasn't
There's
sure.
the directions.
Still.
All right.
I'm not trying to questions, that's all you.
It's just that time.
Well, I've been.
the equation that you established to model this situation,
Oh, yes.
where T represents time in hours.
After it started decreasing, I realized I didn't know.
Okay, so W of 4 is approximately 13.77 grams, and W of 24 is approximately 27.4 grams.
If you're rounding to the third, sixth grade.
No, that's the.
I'm bringing stick figure unless this isn't science.
All right, we do not worry about sig figs.
I didn't see you write it.
Oh, sorry.
It's literally, you can literally teach stick figs in like 5 minutes. They're really easy.
It's like this, it's like 12, how many stick figures are two, there's two numbers.
Yeah.
It's literally, it's, operating instructions.
All right. The next thing we're reviewing, guys, is compound interest.
What?
You guys already know the compound interest formula. A of t, is equal to P, which stands for the principal, times 1 plus rate divided by the number of times it's compounded, raised to the number of times it's compounded times the time in years. Okay? So P, our principal, is our initial investment. R, our rate. We change that percentage and we write it as a decimal. N represents the number of times it's compounded per year. So annually would be 1, semi-annually would be 2, monthly would be 12, daily would be 365, that kind of thing. And T represents time in years. Now, there is... Yeah, we don't have enough time. Okay, what I would do, if we have enough time left in class, is I would assign you all different time periods. So I would start out and I'd say, all right, Anthony, let's say I gave you $1, and yours is going to be compounded annually at a rate of, and I'd give you a rate, and I'd say annually. And then next to you, I'd tell Harry, you're going to do the same thing but semi-annually. And then Claire, you're going to do quarterly. And then Jordan would do monthly. We'd keep going and make smaller and smaller and smaller and smaller and smaller and smaller amounts of time. So eventually we'd get to daily, and then hourly, and then every minute, and then every second, every nanosecond. Okay? And what happens is, as we do that, our multiplier right here would approach this awesome math number called E. Yes, it does. But you're grumpy, so you like to say no. So, all
I
right?
said no to the awesome. I believe it exists.
Okay, so what it does is it approaches E. And what E represents is when it is compounded continuously. Every moment of every second. Yes. All right, and the formula that we use when it's compounded continuously has E as that multiplier. That's our base here. So it's called PERT. P times E raised to the RT. R and T are up here as exponents. There, that looks better. PERT. Do y'all see it? P-E-R-T? PERT?
Yes.
All right. And this is the formula that we use for compounding continuously. If you hit the second button and the divide button on your calculator, guess what pops up?
Hurt.
E. And we need E in PERT. That, saying PERT makes sense.
4.
Do you want us to actually calculate? We could do what I said instead of just talking about if we did it.
Well, you can express the alphabet and just do E.
Why are there so many 8s? On E, there's so many 8s.
I don't know. Oh yeah, I got it. Everything.
Oh, wait.
All right. Okay. Just to show that you remember how, I would like the girls to calculate this scenario. If it is compounding quarterly, I would like the boys to calculate this scenario if calculated daily, and I would like everyone to try our new formula, PERT, to find out what we get continuously. Go.
So wait, how do you spell tasty?
Tastey.
No, but there's no E in it. It's just T-A-S-T-Y. Wait,
I think she's right, but I'm terrible.
It's in the
about
song.
and I was talking about Fergalicious got it wrong.
It's
There's
only,
no E in
it's
it
T.
though.
They're continuing the T to keep it on.
No.
Like T.
Yes, I know, but
Rate.
it's really making me
What's A?
And then change the C's.
Change that rate to a decimal, right?
She doesn't care.
Rate
1.0475. I don't think it's a decimal.
Wait, you 1 times 0 4 1.0 the rate 1.0475 where's the rate 0.0475
.0475.
okay thank you yeah
Yeah, it was kind of at you.
Yeah,
and
got
you
it.
said Bert, and I realized.
Oh yeah,
But apparently Harry heard it. So Harry, if you would like, I could have been having.
What?
Wait, is this a leap year or not a leap year?
It is leap year.
Wait, what do we do for this one?
Do 365, but good question.
Disney.
Claire, no.
okay, I need you to explain this one
What'd you get?
and then you raise it up
Oh.
And you have to count it
Why
up.
am I 10?
Yeah, but it's 3.
Oh, 10 years.
Because that's 10
Sorry.
times 8. Yeah.
Basically, we
Number of
go
times compounded.
Don't be so mean.
what does it mean by compound continuously? That means you just always know every single one.
I feel like I should have gotten.
So is this what you got?
What's this? What's
I
that?
feel like I should have too. Even when you're shooting
I'm sorry. I get those confused all the time.
All right, girls.
I'm thinking about leap year.
Did you get $5,612.32? Yep. All right, gentlemen. Did you get $5,627.88?
Yes.
And all of you, did you calculate continuously to $5,628.05?
Yes.
So daily, just be over 365.
Yeah. Daily would be 365.
Seems like it'd be a bigger number.
You know, you think if you compound it that many more times, but what we notice if we do a table where all we do is change in is to begin with it changes by larger amounts, but then the more minute it's it's almost meaningless. Yes, sir.
Would it like change like when we're doing 4.7 or 0.0475 divided by n, which is 365 for my case? If I like rounded it to a different place, like it's like in half.
Yeah, you wouldn't want to round. Like for your problem, you would punch this straight into the calculator. You would never do any rounding until the end. So you would do this. You would punch divide by button. You'd punch 365. You'd punch the exponent button. Then you do 365 times 10, and you punch it all in at once.
Okay. Yes,
If you do it all at once, you give yourself less chance of messing it up.
Yeah, I rounded it like slightly different, and I was off by like a point. Yes. I was off by like 2.
And since we started with, even though $3,500 is a large amount of money, it's not extremely big. If we started with a larger amount, your error would be a good bit more. Okay, half-life.
Ew.
Yes. Alright, so half-life. What will our population be with respect to time with half-life? Well, our formula is this. P naught. P sub 0. Population at time 0, right?
Yeah.
Population at time 0. So that's what we start with. And if it's half-life, what's my multiplier? A half. Very good. And then we take the number of years, but then we divide it by the half-life period to determine how many times we take half, right?
So is PO or P to the 0
P sub
like the
0.
same thing as A? Right?
Yes, in the other formula. Yeah.
Seems like somebody taught me chemistry.
Could be. Okay, so we have radium-226 that has a half-life of 1,620 years. So if we start with 8 grams of this element, how much will be remaining after 3,000 years? So the population with respect to time of 3,000 years would be the initial amount, which is 8, times 1/2 raised to the number of years divided by the half-life period. So, there is approximately 2.22 grams of radium-226 remaining after 3,000 years.
These are logarithms.
We are going to use logarithms to solve, but what we're going to have later on is, how many years? That's what we're solving for later. Okay? Now let's just talk about this one. We have the population of Rodioville increasing according to this model. So, did you have to come up with a model? No, it's given to you. Now, this is in terms of E, and a lot of models are based in terms of E. We're going to look at a lot of them. But, in this case, T of time 0 is going to represent the year 1985. That was a good year. So what was the population in 1985? 45,000. Yeah. Okay, predict the population in 2005. We're not going to do it, but what would we do?
Just plug in.
Plug in what?
However many years it's been.
How many years has it been? 20. So what we would do is we would take the model that we were given, and because T represents the number of years since 1985, what we would plug in for T, would be 20. And we just punch it in. All right, so your homework is out of your blue textbook. It's 7 through 11. The calendar says 77. That's kind of funny. 7 through 11, 15, 20 through 22, 27, and 28. And that's it.